Good morning. It is 11 o'clock in Philadelphia, and welcome to Thermal Live 2017. I'm Graham Kilshaw with Electronics Cooling Magazine. This presentation you're about to see is called Simulation for Printed Circuit Board Design Reliability, presented by ANSYS. And your presenter today, I'd like to welcome David Gebb, who's one of the application engineering team based in San Jose. Good morning, David.
Hey, Graham. Good morning.
And we're also joined by the Senior Digital Editor for Electronics Cooling Magazine, MP Divakar. Good morning, MP.
Hi, good morning. Good morning all to the Electronics Cooling audience.
And both David and MP are speaking to us from San Jose this morning. So, attendees, before we begin, a little instruction on this webinar platform, which is called On24. If you have any questions during the presentation, you can send those in via the Q&A box at the bottom of your screen. Find the Q&A tab, click on that on the left side of your screen, and that's how you can enter your questions. At any time during the presentation, we'll collect all the questions, and then David and MP will run through your questions and try to answer them at the end of David's presentation. If you do have any technical issues during this presentation, just refer to the yellow tab that has the question mark on it, and most of the common issues can be resolved there. You can also chat with other audience members during the presentation. Hopefully you're still paying attention to David, but you may want to interact with the other people that are listening, and we have a couple hundred of you today. Click on the Group Chat app at the bottom of your screen. See the tab at the bottom that says Group Chat, and you can interact with the other audience members. But don't use that tab, please, if you want to send a question to the presenter. That's really it. If you want to view all of the presentations available at Thermal Live today and tomorrow, you can see a link app at the bottom. If you hover over it on the bottom bar, the one with the chain image, you'll see that it pops up Thermal Live. You can click there and quickly register for all of the other presentations today and tomorrow. And there's also a second chain link image down there. If you hover over that one, you should also be seeing a quick link to the ANSYS webinar, who are the presenters and sponsors of today's presentation. And so with that, I will hand over to you, David.
Okay, thanks, Graham. And thank you to everyone for attending this presentation. So the topic of this presentation is Simulation for Printed Circuit Board Design Reliability. The outline of this talk is presented here. So first, I'll discuss the multi-physics simulation approach to printed circuit board design. And in particular, I'll discuss the electrical, thermal, and mechanical reliability aspects of PCB design. Next, I'll present a sample case. So we'll take a look at an electronics enclosure. And then finally, I'll discuss trace modeling for thermal and structural analysis. This section addresses how to model a printed circuit board for thermal and structural simulations. So a printed circuit board is a complex device, and you have many layers, traces, and vias. So how do we model this for thermal and structural analysis? This will be discussed in the last section. Okay. So a lack of a good power distribution network design of a printed circuit board can lead to high current densities, elevated temperatures from joule heating, and eventual product failure. These concerns are especially relevant for high current PCBs that are densely populated with components, and for PCBs with reduced trace and via dimensions. Simulation can help ensure printed circuit board design reliability. It's important to run a DC voltage drop simulation for a printed circuit board to ensure clean and sufficient power is supplied to each of the devices on the board. It is also important to run an electrothermal simulation for a printed circuit board to ensure critical temperatures are not encountered. So here, Joule heating effects in the copper traces can lead to increased temperatures, and this can cause printed circuit board and component overheating. Now, by electrothermal simulations, I mean performing thermal simulations with Joule heating effects taken into account. And finally, it is important to run thermomechanical simulations for printed circuit boards to ensure structural integrity of the board and components is maintained. So here, elevated temperatures can lead to thermal deformations, and this can cause component failure and or PCB delamination and failure. And by thermomechanical, I mean bringing the temperature from the initial thermal simulation into a structural simulation to calculate deformation. So this emphasizes the importance of DC, thermal, and structural simulations for printed circuit board design reliability. This presentation will focus on the electrical, thermal, and structural reliability aspects of printed circuit board design. For electrical reliability, power and signal integrity analysis is required, and this can be provided by ANSYS SI-Wave. For thermal reliability, a thermal analysis is required, and this can be provided by ICEPAC. For mechanical reliability, a stress analysis is required, and this can be provided by ANSYS Mechanical. Now, these three tools, SI-Wave, ICEPAC, and Mechanical, need to be linked. So the Joule heating losses from SI-Wave need to go into ICEPAC for the thermal analysis. The thermal analysis from ICEPAC needs to, the information from the thermal analysis needs to go back into SI-Wave so you can update your Joule heating losses based on the updated temperature. And this requires a bidirectional connection. So increased temperatures leads to increased resistances and more Joule heating. Additionally, the temperature from ICEPAC, once converged, needs to go into ANSYS Mechanical for a thermal structural simulation. So thermal issues really lie at the center of this workflow. In the next few slides, I'm just going to go over these three tools, SI-Wave, ICEPAC, and Mechanical, to give you some background, and then we'll head on into discussing the general workflow and consider a sample case. But SI-Wave provides power integrity, signal integrity, and EMI analysis of a complex PCB or electronic package. SI-Wave DC can determine the direct current voltage drop and power loss per layer. It can determine the DC resistance of power planes, ground planes, and signal traces. It can also determine the DC current direction, including return paths, as well as DC current magnitude into and out of vias. SI-Wave DC quickly identifies high power loss regions in your board. It identifies where current crowding is occurring in the copper and identifies high currents in vias. And SI-Wave employs a 3D finite element field solver with adaptive meshing to compute these DC currents and voltages in the PCB. ANSYS ICEPAC is an integrated electronics cooling solution for IC packages, printed circuit boards, and complete electronic systems. IcePack solves for fluid flow and heat transfer. IcePack has a number of additional capabilities as well, and some of these are listed here. One important capability of IcePack is its ability to perform multi-physics couplings with other physics solvers from ANSYS. So in this diagram on the bottom right, you see IcePack sitting at the center of some coupled physics analyses. So IcePack can link with ANSYS HFSS, Maxwell, and Q3D, as well as SI Wave for electromagnetic thermal simulations. IcePack can also link with mechanical for thermal structural simulations. IcePack can link with ANSYS Apache chip-level software to bring up chip-level power maps into the system level for thermal simulations in IcePack. And finally, IcePack can link with ANSYS Simplor for more advanced reduced order modeling applications. So in this talk, we'll be discussing some of these links, in particular IcePack to SI Wave and IcePack to mechanical for electrothermal and thermal structural simulations. And finally, ANSYS mechanical can be used for thermal structural simulations. Now, ANSYS mechanical can perform a breadth of analysis types, and some of these are listed here. In this presentation, we'll be using it for a thermal structural simulation. Now, these three tools need to be linked for an electrothermal and thermal structural simulation. In particular, SI Wave will calculate the electrical DC losses, and it will transfer these into IcePack for a thermal analysis. IcePack will calculate temperatures and then send these back to SI Wave, where a new electrical DC analysis will be performed and new conductive losses will be calculated. These, in turn, will go back into IcePack, and an updated temperature map will be obtained in the board based on the updated conductive losses. This cycle continues until thermal convergence. So once SI Wave and IcePack have converged, the temperature map can then be exported to ANSYS mechanical for a thermal stress analysis. This is the workflow that I'll go through for the sample case. So let's consider this problem setup shown here on the right. Here, there's a PCB that's oriented vertically in an enclosure. So gravity is pointing down. Air circulates via natural convection in this enclosure. A liquid cold plate cools one IC package on the left there, and a heatsink cools the other package on the right. All three modes of heat transfer are modeled, and the joule heat dissipated in the board is mapped from SI Wave into IcePack. Additionally, in the sample case, there's several additional components that are generating heat, and those are listed here. So this is the problem setup for this sample case. Now, the first step is to import the printed circuit board layout into SI Wave, and then define the excitations there in SI Wave. Once that's been done, a DC voltage drop analysis is run for the board in SI wave. From this DC voltage drop analysis, we get voltage and current density as shown here. Voltage on the left, current density on the right. And we get this for each layer of the board. So we have current densities in each layer of the board here, as well as voltages. Also, we get current density through the vias as well. Additionally, from the voltage and current densities, we get the power density as well. And the power density is shown on the left. On the right is the power map that is transferred into IcePack. And this power map is obtained at each level, at each layer in the board. So this layer by layer power map will come into IcePack to account for joule heating in the board. And this power map was generated in SI wave from a DC voltage drop analysis. The current crowding in traces, planes, and vias leads to high joule heating losses in the printed circuit board. The layer by layer joule heating power maps from SI wave are transferred into IcePack. On the left is the SI wave power map, and on the right is the power map that comes into IcePack at each layer in the board. So this SI wave DC coupling with IcePack is shown here. The spatial power loss information from the DC voltage drop analysis in SI wave is transferred into IcePack as a spatial joule heating map. And then the spatial temperature information from the thermal analysis in IcePack is transferred back to SI wave and interpreted as spatial thermal modifiers for electrical conductivity. The coupling between SI wave and IcePack is automatically performed by this coupling iterator shown here. And this coupling iterator proceeds until you get thermal convergence. To set up the coupling iterator, in this panel, you just specify the SI wave project directory and project name, and you specify the printed circuit board in IcePack corresponding to that SI wave project. Finally, you set up termination criteria, and you click Accept to run. The SI wave IcePack automatic coupling proceeds until thermal convergence. So in this image, we have the electronic system in IcePack. And here is the converged natural convection flow field velocity vectors. And you can see the circulation through the enclosure due to natural convection. So it's important to note for this thermal simulation in IcePack, the traces were imported into the PCB. So why is it important to import the traces into the printed circuit board? The key here is to account for local variation in thermal conductivity and heat spreading. So importing these traces allows you to account for heat flow paths in copper traces that you cannot account for if you don't include the trace geometry in your analysis. The converged temperature results on the board are shown here. And if we zoom in on the package under the cold plate, we can see the particle traces, the temperature on the chip, the temperature on the package surface. And again, as was the case for the printed circuit board, traces were also imported into the package. And again, this accurately accounts for local variations in properties. Important for thermal simulations is thermal conductivity. And it will vary significantly depending on the layout in the board or the package. And we'll talk more about how to model printed circuit boards in the last section. And in particular, how to incorporate the effects of these traces. Here's the temperature on the solder balls in the converged ice pack simulation. And we can even zoom in further and look at the temperature profile on the chip itself. So this slide kind of emphasizes why it's important to include a Joule heating analysis for the printed circuit board. In this case, without Joule heating, the maximum temperature was 86.6 C. And you can compare that to the maximum temperature when the SI wave ice pack coupling was performed. That temperature was significantly higher, about 103 C. The DC power consumption increases as well when you include the effects of Joule heating in the board. This contrast underlines the importance of considering the effects of Joule heating in the printed circuit board. Accounting for temperature will also have an effect on the resistance and resistive losses calculated in SI wave. So shown in this red box are the loop resistances calculated in SI wave at a 20 degree C ambient temperature. And those are compared to the loop resistances when you import the ice pack temperature map into SI wave. When you account for temperature, these resistances increase significantly by about 30% uniformly in this example. And again, these resistive losses will in turn have an effect on temperatures. So a bidirectional coupling between SI wave and ice pack is necessary. And this allows for iteration until thermal convergence. Now, before I move on to the mechanical side of things, I just want to mention here that there's a couple options for launching this electrothermal analysis. You can launch it from ice pack, and you can also launch it from SI wave. Both ways are fully automated, so the coupling proceeds automatically until convergence. Also, both ways allow you to perform either a conduction only or a full CFD simulation. In the sample case, I showed you a full CFD simulation where we accounted for a relatively complex thermal environment. If you don't want to take into account such a complex thermal environment, you can simply perform a conduction-only analysis. And this will be much quicker, but it requires an assumed thermal boundary condition on the board. For a conduction-only analysis, you can input a heat transfer coefficient boundary condition on the top and the bottom of the board, or you can specify that heat transfer coefficient in terms of a known correlation. And there are some built-in correlations here that you can. So two options, they're basically equivalent. A thermal engineer using IcePack may want to launch this electrothermal analysis from IcePack, and a EE may prefer to launch it from SI-Wave. So I've discussed this electrothermal approach using SI-Wave and IcePack. And the next step here in this workflow is to discuss the mechanical side of things, the thermal stress analysis. The IcePack temperature data is mapped into mechanical. For the sample case, 5 holes were simply supported. Materials were defined, and the mechanical simulation was performed. Thermal deformation can stress the solder joints and even crack them, causing open circuits or intermittent errors. Here is a picture of the total deformation in true scale and magnified scale. This is for the system, the board and the components. We can also look at the package under the cold plate and look at total deformation on the package, or in particular on the solder balls. So again, as was the case for the IcePack thermal analysis, we're importing the traces into ANSYS Mechanical to accurately account for local variation of material properties. And this is crucial for a structural simulation of a printed circuit board. The equivalent stress in this board is shown, and the equivalent stress on the package under the cold plate is shown. And finally, some pictures of the directional deformation, true scale and magnified scale, along with the equivalent elastic strain in the package. So in both the IcePack thermal simulations and the mechanical structural simulations, I mentioned that the traces were imported and accounted for. In this last section, I'll just discuss how to model traces for thermal and structural analysis. Before I go into that, I just want to recap some PCB geometry basics. So a PCB is composed of a stack-up. This is the layers of material that form the board. These layers are a combination of dielectric and metal. The dielectric could be FR4 and the metal could be copper. Traces and planes on the board route signals within a metal layer. Vias are metal interconnects between layers. Now, electrical CAD or ECAD data and geometry describes the PCB layout. This can be compared to mechanical CAD. ECAD describes the PCB layout, and a number of vendors provide layout capabilities and layout file types. ANSYS can import virtually any file type for the board layout and incorporate this into a thermal or structural analysis. So the ECAD is basically the file that describes the stack up traces and vias in a board. Now there's I'll talk about three different approaches for modeling a printed circuit board for thermal mechanical simulation. The lumped board approach is the simplest. In this approach, you would just assign orthotropic properties for the in-plane and normal directions. So for a thermal simulation, you would specify in-plane thermal conductivity and normal to plane conductivity. And these values are uniformly assigned throughout the board. This approach is useful for system-level setups when the board performance is not the primary focus. This lumped approach is easy to implement and leads to a reduced solve time. I plotted the lumped approach here on this speed versus accuracy graph, and you can see it's in the top left. Good speed, but the accuracy is sacrificed because when you use the lumped approach, you're not going to be able to account for detailed heat flow paths in the printed circuit board. An alternative is the explicit geometry approach, where you model the geometry of traces, planes, and vias in full detail. This approach results in high accuracy. However, the downside here is, in addition to a very long preparation time, potentially, you also have a large mesh size that leads to long solution time. You'll need a large mesh to capture the explicit geometry. So this is plotted on the other end of the spectrum. Good accuracy, but speed is poor for this explicit approach. A third approach is the ECAD approach, where the metal fraction in each layer is mapped from ECAD data. This approach requires the import of an ECAD file, but it leads to both highly accurate and fast solutions. So you get the best of both worlds with the ECAD approach. And I'm going to discuss this ECAD approach in more detail. First, let's compare the ECAD approach to the explicit approach. We can do this by considering this package where the ECAD model was imported. So the traces were imported from ECAD onto this package. On the right is an explicit representation of the package. So how does the ECAD and the explicit model compare? The ECAD model has dramatically less number of objects, less mesh count, and less preparation time than the explicit model. So this kind of underscores the speed benefit of the ECAD approach. So with it being much faster than the explicit approach, what about its accuracy? How does it compare in terms of accuracy? So we can compare accuracy for the ECAD approach and the explicit approach by measuring the junction to board resistance for each of these packages. The junction to board resistance in the ECAD and explicit models are nearly identical, about a 0.7% error in this case. And refining the mesh in the ECAD model further will deliver closer results to the explicit model. So accuracy is maintained with the ECAD approach as well. So in addition to being much faster than the explicit approach, the accuracy is not sacrificed. Let me just briefly describe the ECAD approach in a little more detail, and that'll just be a few more slides on this. So in the ECAD approach, a grid cut computes the metal fraction content on a separate background Cartesian grid. The metal fractions are used to determine the orthotropic conductivity at each cell in the CFD mesh. Here you can see the CFD mesh overlaid on the grid cut metal fractions for a given layer in a PCB. We can zoom in to this region and look look at it in more detail. So here you can see in more detail that the black lines are the CFD mesh, the blue squares are pure FR4, and the red squares are pure copper. As the grid cut is refined, it approaches the ECAD geometry. The recommended grid cut mesh size is on the order of the minimum trace width. And it took about 100 seconds to calculate the metal fraction for this board. You can compare the metal fraction on the left from the grid cut calculation to the original geometry on the right. Additionally, as the CFD mesh is refined, the conductivity improves. The recommended CFD mesh size is 4 times the grid cut for board level models, or in other words, about 4 times the minimum. For system level models, it's 8 times. You can see in this image the thermal conductivity map compared to the original ECAD geometry on the right. Okay, with that, I'd like to wrap up and just provide some concluding remarks. Multiphysics simulation of printed circuit boards provides an accurate and comprehensive approach to ensuring design reliability. A DC solution provides information on power delivery and power dissipation for thermal analysis. The thermal solution identifies hotspots and provides temperatures for both the DC and mechanical solutions. And finally, the mechanical solution determines thermal deformation and stresses. The multiphysics simulation approach to printed circuit board design can increase product reliability while reducing cost and time to market. If you visit ansys.com, you can go to the events page and take a look at upcoming events. There may be one in your area. The events page also includes webinars that you can access from anywhere. You can also visit the Ansys resource library on ansys.com for more information on this topic or other topics. There's white papers, webinars, a large amount of information on technical and simulation topics at the Ansys resource library. And finally, if you found this topic interesting, I would encourage you to check out the 6-part video series that's on YouTube, Ansys Electrothermal Analysis of a PCB. So it's a 6-part video series. It goes into the DC voltage drop simulations for a board, then it goes into the thermal simulations, and then the mechanical simulations. So I'd encourage you to check that out if you found this topic interesting. And with that, I want to thank everyone for your attention. And MP, do we have any questions?
Yes,
Thanks, David. That was a great presentation. I'm just looking at our attendee list here, and I see we've got folks from all over the world today. Europe, Asia, and North America are all included. We're seeing folks logged on from just a handful of companies here to mention: LG, Johnson Controls, Thales, Northrop Grumman, Xilinx, Cisco, Fujitsu, and Toyota, just to mention a few out of the couple hundred that are registered today. And with that, I'm going to hand over to MP Divakar. We've had some very interesting questions submitted. MP, do you want to take the questions here with David?
Yes. First off, excellent presentation. I thoroughly enjoyed it. So I have one, and I'll start off with that and then defer to all the audience questions. Question on the integration between the 3 simulation tools you mentioned. Is that through file exchange, or they're all directly addressable through DDE or some other means of interaction?
Yeah, so this is through file exchange. So the SI wave ice pack coupling is done automatically in the background. So users don't need to manually import files between the two tools. So SI wave and ice pack is done automatically in the background. Ice pack to mechanical is done through an automatic transfer in ANSYS Workbench. So most of this file transfer is behind the scenes. Users would just need to launch the SI wave ice pack coupling iterator on, let me pull that up, for the electrothermal analysis. Just launch this iterator, and most of the, and all of the file transfers behind the scenes. This coupling iterator here. And then for mechanical, it's in Workbench.
There is a question from the audience on how the traces are imported. Are they physical solids or imported as surfaces and then thickness added on later?
So the traces are imported for example, in IcePack, you would import the trace file, the ECAD file, so it could be a BRD file or an ODB++ file. You would import this onto a PCB object in IcePack. So there's, on the PCB object edit panel, you would just say import ECAD file and choose the ECAD file. And that would bring the ECAD file in onto the board. Now, once that ECAD file is in, that ECAD file describes the complete geometry of the traces and the layer stack up and everything. It describes everything. Once that's into IcePack, IcePack computes the metal fraction, the detailed metal fraction from that ECAD file. And it's that metal fraction that IcePack uses for the CFD simulation. So it takes the ECAD file, which describes the geometry and exact detail in the board, and computes a metal fraction. And then that metal fraction is used in the CFD analysis. And similarly for mechanical.
Okay. So we have another question. That is on, how do you iterate with different values of convection coefficient, from low to high, and then figure out whether the conjugate heat transfer is important to include or ignore?
Yeah, so if you want to look at different heat transfer coefficients and how they affect the solid phase temperature, you can do it parametrically. For this case, you would just set up a number of these electrothermal analysis and input different heat transfer coefficients if you're doing a conduction-only analysis. So my impression is this is related to a conduction-only analysis this question is related to a conduction-only analysis where you specify the heat transfer coefficient. In that case, you would manually specify it and perform multiple SI wave ice pack simulations. And
so we have another question on the VS in the PWB. The VR modeling, is it available for all of the components, or is it limited to only a few components in the simulation?
So the VIA modeling, VIAs will come in with the ECAD file. So you would set up the VIAs in your PCB layout tool, and you would set them up there in your PCB layout tool. And whatever you set up there, you will just import into IcePack as an ECAD file. So it's similar to IMCAD. You may use SolidWorks or another IMCAD tool, and then you import it into IcePack. You would also import that ECAD file with VIAs defined into IcePack. So you would set it up ideally within the ECAD tool. There's also options for modeling VIAs explicitly in IcePack. But the preferred approach in terms of speed and accuracy is just to model those VIAs in your PCB layout tool and then import them straight to IcePack with the ECAD file.
So we have another interesting question. This relates to the flow between the three simulation tools. The question is, can we import the ECAD data directly into ANSYS Mechanical?
Yes. So that's a supported feature since 17.0. So you can import the ECAD into ANSYS Mechanical in the same way that you do for ice pack. And that was what was done for the sample case here. And the background in terms of what's being calculated is analogous to what's done in ice pack. So the ECAD traces are imported, then a metal fraction is computed, and this is used on the FEA mesh to calculate deformation and stresses.
There's another question on performing conduction-only analysis using ANSYS Mechanical. And I know this is a feature that's been around for a long time, for many, many decades, as far as I can remember. That is still available to ANSYS users, right? If you perform conduction-type heat transfer only?
Yeah, it is. Yeah, it's still available. Okay. So you can do a conduction-only analysis with ANSYS Mechanical.
Okay. I have one more question, from my side, and that is going back to the file exchange and the interaction between the three tools. How do you reconcile and map the finite element or the finite volume grid between the three tools?
Yeah. So, for example, when you're mapping temperature from ice pack to mechanical, the temperature map is on a CFD mesh, and it's being mapped to the mesh in mechanical. So the meshes are different. So there's interpolation that takes place to accurately map temperature from one mesh, a CFD mesh, onto another mesh, a mechanical mesh. Okay. So there's some interpolation that's used.
A more broader question here. A user is wanting to know what's the best way to find the convection coefficient of the surfaces in the model.
Yeah, there's a few different ways to do this. One way is just to run a CFD analysis. If you're running CFD, you don't need to worry about specifying a heat transfer coefficient. However, if you are handy with convection coefficient tables and heat transfer textbooks, you can just refer to those. I'm sure there's some good tables on electronicscooling.com, the electronics cooling website, and also in just heat transfer textbooks. I think there's a lot of information on convection correlations, and so if you're familiar with that information, you can just refer to those tables. They're usually specified in terms of a Nusselt number versus a Reynolds number, and you can determine what the heat transfer coefficient is for that convection scenario. So two options: just run the CFD analysis, don't worry about it, or do a little bit of homework and find what the appropriate heat transfer coefficient would be in that case.
There is one more question from a power electronics engineer, looks like. They're wanting to know what type of simulations does one need to perform, for a power supply like a buck converter or a boost converter. I know this is more of an application-specific question, so I'm not sure if you have an answer for this.
For a thermal simulation for this type of application?
Yes.
Yeah, this would be some. I think at a minimum you would do a CFD thermal analysis for this type of application. I think if this user could reach out to us and let us know some more details, I think we can give a better answer to how to approach that type of application.
Okay. There were a few questions regarding pricing, and they can follow up with you separately on that, right? Pricing for SI wave and ANSYS, mechanical and other tools.
Yeah, sure. They can follow up separately.
One more question. I think we have a minute or two left, and let's try to get as many as possible. The trace geometries, can you import them from GDS to file format?
Could you repeat the file format?
Yeah, the GDS2. This is mostly the chip layout file format. I would imagine one has to go through conversion to bring them into SI wave, or does SI wave directly read GDS to file formats?
My my hunch is it probably can, but I cannot say for sure. I would have to follow up with an SI wave expert to get a certain answer to that. But I don't think there's too many issues with bringing in different file formats. It's pretty universal in what file formats can come in. But for this particular file format, I'd have to confirm. Maybe if maybe I can follow up with this user.
Okay. I mean, from my side, I can answer that partially, I think, and that is one has to flatten out all the entities and then convert them, from GDS to DXF, which is probably the preferred route. I think we have one last question, and then we have to wrap up. This would be, okay, I think it's the same. A couple of repeats. Okay, so this is a question on the component model. Can you get detailed component models in SI wave, or do you approximate them, especially the package models?
In SI wave, I'm not sure on the answer to that. That's another SI wave question I would need to defer to an SI wave application engineer. I apologize. I'm not sure on that.
Okay. Well, that does it. We have to wrap up. And thank you for a great presentation. I'd like the audience also, to follow up on any other, questions or information you need. Again, I thoroughly enjoyed it, and have a good day, good evening all. Thank you. Bye.